Good afternoon, ladies and gentlemen. I am honored to be invited by the president of Sigma Xi to talk about innovation. I have a favorite mantra for that, which I would like to tell students and junior researchers in the audience. Most students and postdocs generally follow what their research mentor tells them. Although that may be good training, additional efforts are needed in order to develop an innovative mind. How can one develop a mindset that promotes innovation? Consider the Schrödinger equation. How did it dawn on Schrödinger to have second derivatives with respect to space, but only the first derivative with respect to time? Even more, how did Dirac decide to take the first derivatives with respect to both space and time? There must be some pattern that Schrödinger and Dirac must have discerned. Where others saw a frog, they saw a horse. Consider the equations of electromagnetics before James Clerk Maxwell. The two curly equations did not seem to match. Maxwell saw a hole in the first curly equation, and he correctly filled it. The rest is history. It is the discovery of the hole by Maxwell that gave me the first clue towards developing an innovative mindset. So, let me tell you a tale. And I will follow the advice given by the king to the white rabbit in the book Alice in Wonderland. So I'll begin at the beginning and continue till I reach the end. I've been interested in curves from as far back as I can remember. Many curves have a property called handedness, which you can appreciate by contrasting a right-handed seashell with a left-handed seashell from the same species, the Florida lightning whelk. Curves and chirality or handedness underlie most of my research during the last 40 years. Light can have chirality. In air, it can be either right circularly polarized or it can be left circularly polarized. In air, light of either chirality moves with the same speed, and the attenuation rate for both chiralities is minuscule. In 1992, I came across a mineral called ulexite. It is opaque, except when you view through it along a specific direction, then it is quite transparent. A scanning electron micrograph shows the structure of ulexite. It is like a mass of parallel and straight glassy fibers all stuck together. One can see along the lengths of the fibers, but not in directions transverse to the fiber lengths. I called my colleague Russ Messier. He was one of the pioneers of morphological studies in thin films. I asked him if similar substances can be made in a laboratory. He said, yes, of course. And with that answer of his, a whole new world opened up for me. Russ explained to me the industrial process of physical vapor deposition, which has been around now for over 160 years. Put a source material in an evacuated chamber. The source material shall evaporate if you heat it. Collect the evaporant flux on a substrate. A thin film is formed on the substrate. If the conditions are right, nominally parallel columns or nanowires or nanocolumns grow. This assembly of nanocolumns is called a columnar thin film. Here is a scanning electron micrograph of a columnar thin film of zinc selenide. So I asked Russ if we could rotate the substrate during deposition. He said, of course. Well, then I said, rotate the substrate about a central normal axis passing through it, and nanohelixes will grow instead of nanocolumns. That is what you see in this scanning electron microscope image from 2018. Note also the structural periodicity in the thickness direction. Also, I said to Russ, rotate the substrate about a tangential axis and nano zigzags will grow instead of nano columns. That is what you see in this scanning electron microscope image from 2017. This film is also structurally periodic in the thickness direction. Finally, it should be possible for both kinds of rotations simultaneously in order to get complex nanomorphologies. And that is what you see in the films labeled B2E from 2013. Structural periodicity is maintained in these films too, in the thickness direction. These scanning electron microscope images are of films made in this century. Back in 1994, after I had explained the concept to Russ Messier, the issue arose as to how would that concept be implemented. Russ advised me to call Michael Britt at the University of Alberta. His collaboration and mine resulted in a chiral sculpture thin film comprising nanohelixes. That was in 1995. And that is how the area of sculpture thin films began. I am a theorist. However, in 2008, I set up a thermal evaporation system. And if I can do that, architected nanocolumnar morphology is easy to realize. Certain changes in morphology can be made, as you can see in this scanning electron microscope image. The change of shape can occur within 20 to 30 nanometers of growth, which is optically abrupt. This is because sculpture thin films comprise 1 to 3 nanometer clusters as building blocks. The intercolumnar as well as the intercluster porosities can be controlled by varying the deposition conditions. Many integrated optical devices become possible thereby. Let me talk about a few. In presenting optical applications, let me concentrate on chiral sculpture thin films, which are forests of parallel nanohelixes. These chiral sculpture thin films can function in optics as circular polarization filters. If a chiral sculpture thin film is structurally right-handed, it preferentially reflects right circularly polarized light incident on it in a wavelength range called the circular Bragg regime. This regime is identified as the dark blue band in the spectrogram on the left. The right-handed chiral sculpture thin film does not reflect left circularly polarized light in that regime, and so the spectrogram on the right does not have that blue band. Therefore, a chiral sculpture thin film, which is structurally right-handed, functions as a band-stop filter for right circularly polarized light. If a chiral sculpture thin film is structurally left-handed, it preferentially reflects left circularly polarized light in the circular Bragg regime, but not right circularly polarized light. And so it functions as a band-stop filter for left circularly polarized light. Suppose we cascade a structurally left-handed chiral sculpture thin film and a structurally right-handed chiral sculpture thin film that are otherwise identical. Then we get a band-stop filter for all polarization states, and you can see that blue band in both the left and the right spectrograms. And if both handednesses are intertwined period by period, again we will have an all polarization band stop filter. And therefore again you can see in the spectrograms there are blue bands in both of them. If we wish to shift the circular Bragg regime after deposition, one way would be to anneal the chiral sculpture thin film. Annealing alters the morphology. Here are scanning electron microscope images of a titanium dioxide chiral sculpture thin film before and after annealing. The morphology changed due to annealing. The effect of annealing is a blue shift of the circular Bragg regime. The black curve indicates the circular Bragg regime before annealing. the red curve after annealing. The red curve is blue shifted with respect to the black curve. Multi-band circular polarization filters can be made by growing a stack of different chiral sculpture thin films. Changkwan Huangbo in South Korea grew a stack of 3. As predicted by theory, there were 3 circular Bragg regimes. Thus, one can envision many-sectioned sculpture thin films as entire optical systems. Another example, you can see a 90-degree central twist defect in a chiral sculpture thin film incorporated during fabrication. This was done deliberately. The substrate was rotating at a normal speed. All of a sudden, it was rotated by 90 degrees very rapidly, and thereafter rotation at the normal speed was resumed. The effect of the 90-degree twist defect is a transmittance spike in the spectrum. This transmission spike indicates a reflection hole. The circular Bragg regime is generally 50 to 100 nanometers wide. The spectral hole is about 10 nanometers wide. Controllable sources of circularly polarized light can be made. A chiral sculpture thin film was fabricated with a central defect. This defect comprises 2 spacer layers sandwiching a layer of quantum dots that were optically excited. Thereupon, visible circularly polarized light was emitted. Since the chiral sculpture thin film was left-handed, a spectral hole showed up in the reflectance spectrum for left circularly polarized incident light when the quantum dots had not been excited. When the quantum dots were excited, the emission spectrum had a peak for left circularly polarized light. In a different experiment, a columnar thin film serving as a quarter wave plate and a structurally right-handed chiral sculpture thin film were grown on top of one mirror of a vertical cavity surface emitting laser. The laser was pumped electrically. It emitted right circularly polarized light of 848 nanometer wavelength and line width of about 1.06 nanometers. Next, suppose we have a chiral sculpture thin film grown on top of a metal film. The interface can guide more than one surface wave. These surface waves are called surface plasmon polariton waves. And when it guides more than one surface plasmon polariton waves, they have all different characteristics, even though the frequency is fixed. This had been theoretically shown in the year 2008. It was experimentally confirmed the following year. In the usual prism-coupled configuration of Kretschmann and Rather, in the angular spectrum that I have shown on the right, the 2 arrows point to the excitation of 2 different surface plasmon polariton waves at the same frequency. Now, this phenomenon can be exploited for optical sensing. Here you can see angular shifts with sugar concentration in sweet water that infiltrates the chiral sculpture thin film. Let me pause here to assure you that all experimental results I have presented so far have been validated against theoretical studies involving the solution of Maxwell equations. But I am not going to inflict equations on all of you. Please see this book if you are interested. Let me return to experimental results. In order to sense immunoglobulin G in water, a nanoparticle layer of gold was deposited between 2 chiral sculpture thin films, and protein A was bound to the gold nanoparticles. Then aqueous solutions of different concentrations of immunoglobulin G were put inside the chiral sculpture thin film, and the reflectance versus angle of incidence data were measured at 633 nanometer wavelength. These data were used to train a support vector machine. The system could then be used to predict the concentration of immunoglobulin G of an unknown sample with at least 93% accuracy. About 2 years ago, with Manik Pradhan of Kolkata, I began researching the spin-dependent splitting of light in the photonic spin Hall effect induced by the Pancharatnam Berry phase. We used the quantum weak measurement technique. Although published, the results are too undigested for presentation in this talk, except that both the Pancharatnam Berry phase and the spin-dependent splitting of light were found to be significantly affected by the columnar morphology. Our investigations continue. Next, by depositing sculpture thin films on substrates that have been lithographically patterned, the nanoscale and the microscale can be blended, as in the metal sculpture thin films you can see here, and these dielectric sculpture thin films. These structures could be useful for photonic bandgap engineering, for labs in a chip, etc. One of my students is currently investigating these three-dimensional photonic crystals. Here I show you a columnar thin film of silver deposited on a topographic substrate with parallel ridges. Asymmetric diffraction took place during optical experiments, leading to a simple method for fabricating glazed gratings. We are able to coat even such complicated substrates as a butterfly wing and an entire fly, in an aim to develop copycat technology. Let me use a child's toy called round pinpoint to illustrate my approach to bioreplication using sculpture thin film technology. On the left is a collection of parallel cylindrical pins standing upright over a plane surface. On the right is the same collection of pins over an undulating surface. The tops of the pins reproduce collectively the substrate features. The smaller the cross sections of the pins, the better is the top surface reproduction of the substrate features. In order to grow upright columns, we can still use the same technique as before, but the substrate is made to rotate very rapidly at about 1 revolution per second, and in that case, instead of nanohelixes, upright nanocolumns grow. This is a key step in a bioreplication technology. We begin with a biotemplate. Deposit on it a columnar thin film comprising upright columns of nickel. Electroform that nickel columnar thin film to thicken it for mechanical sturdiness. Then we remove the biotemplate and we now have a die or a mold for stamping or casting. On the left you see a cornea of a blowfly. On the right is its bioreplicated copy made of PVDF, a polymer. Note how good is the replica. A real success of bioreplication came in the fight against the spread of infestation of emerald ash borers. This pest species from northeast China is decimating ash trees of some 25 species in both the United States and Canada for just about a quarter of a century. My group used our bioreplication technology to make decoys labeled C to E of the insect A. These decoys of female emerald ash borers were used to lure male emerald ash borers for mating. Female emerald ash borers as well as their bioreplicas were stuck to adhesive sheets in order to lure male emerald ash borers flying overhead. Our bioreplicated decoys were 40% more successful than dead females in luring male emerald ash borers. Another extension was to develop latent finger marks. Finger marks on transparent glass are not always easy to see, but when a columnar thin film is deposited of the right material, the finger mark is developed and it can be seen. You can see the ridges and you can even see pores inside the ridges. This scanning electron microscope image shows the columnar thin film that grew on top of the finger mark residue. This method was successful even in exposing latent finger marks on cartridges after discharge, and also on compact discs, as well as polymer banknotes. Finger marks often contain DNA. Here is a partial bloody finger mark that was developed by depositing the columnar thin film of a chalcogenide material on top of it. Subsequent DNA analysis showed almost perfect identification of the donor of the partial bloody finger mark. With that, I will stop talking about my research on architected columnar morphology and return to the issue of innovation. Analyzing the progress on this research topic, I stumbled on 3 steps that could help one become innovative. The first is to make looking everywhere a constant habit. Every pebble that you encounter must be turned over. The second is to keep on learning, because chance favors the prepared mind, according to Louis Pasteur. The third is to organize, because then you find holes as well as organizing principles. The organizing principles help fill the holes, and they also help looking for completely new phenomena. The Organized Mind. This book was written by a neuroscientist named Daniel Levitin. He argues that organization of the mind is a key asset of highly successful people. He also argues that organization is not the antithesis of creativity. Creativity is ineffective without sufficient organization. As an example, Michael Jackson employed a full-time archivist. Another example, John Lennon archived tapes of songs in progress, carefully labeled. In the course of my research on architected columnar nanomorphology, I looked, I learned, and I organized. With this triple action mantra, I am confident that anyone can become a techno-scientific rock star. Before concluding, let me say that over the last 30 years, I have been immensely helped by colleagues at Penn State and throughout the world, as well as graduate and undergraduate students in this research. And with that, I wish may you be ever more innovative. Thank you for listening to me.